AI Dominion. Welcome, dear viewers, to an exploration of the cutting-edge realm of hyperdimensional computing in artificial intelligence. This journey will take us through the intricate workings of this revolutionary computational paradigm, its applications in AI, and the challenges it faces. So, let's set the stage with a brief introduction to hyperdimensional computing. Hyperdimensional computing is a computational approach that represents information as high-dimensional vectors. While seemingly abstract, this concept is inspired by how our brains process information. The human brain doesn't operate in binary but deals with a multitude of dimensions in its neural networks. Hyperdimensional computing seeks to emulate this, offering a new way to handle complex, non-linear problems that traditional computing methods struggle with. The concept of hyperdimensional computing is rooted in the principles of vector symbolic architectures, VSAs. VSAs utilize high-dimensional vectors to encode symbolic structures, enabling the representation of complex relationships and patterns. This significantly differs from traditional computing methods, which rely on binary logic and linear data processing. The shift to a high-dimensional vector space opens up a whole new world of possibilities, allowing for the representation and manipulation of complex, hierarchical structures in a previously unimaginable way. To truly understand hyperdimensional computing, we must delve into the mathematics underpinning it. This paradigm represents data as points in a high-dimensional space, often several hundred or thousand dimensions. These points, or vectors, can be manipulated using mathematical operations such as addition, subtraction, and multiplication. The beauty of this approach is that relationships between data points can be encoded in the geometry of this high-dimensional space. This allows for efficient data processing and storage, making it a powerful tool for artificial intelligence. The mathematical operations used in hyperdimensional computing are not the standard operations we're familiar with from school. Instead, they are operations defined in the space of high-dimensional vectors. For example, adding two vectors results in a new vector geometrically located between the original vectors. The exact location depends on the dimensions of the vectors and the specific values in each dimension. Similarly, the multiplication of two vectors results in a new vector that captures the relationship between the original vectors. Now, let's explore the applications of hyperdimensional computing in AI. One of the key areas where this approach shines is in pattern recognition. Traditional machine learning algorithms often struggle with recognizing patterns in large, complex datasets. However, hyperdimensional computing can capture subtle patterns and correlations that other methods might miss by representing data as high-dimensional vectors. For example, the natural language processing (NLP) field. In NLP, words can be represented as high-dimensional vectors in a process known as word embedding. The geometric relationships between these vectors can capture semantic and syntactic relationships between words, leading to more accurate language models. This has been used to create more efficient and accurate language models, leading to breakthroughs in machine translation, sentiment analysis, and other NLP tasks. As we delve deeper into hyperdimensional computing, we encounter a formidable adversary, the curse of dimensionality. This term, coined by mathematician Richard Bellman, refers to the exponential increase in volume associated with adding extra dimensions to a mathematical space. In the context of hyperdimensional computing, it translates to a significant increase in computational complexity as the dimensionality of the data increases. Each operation on these high-dimensional vectors requires substantial computational resources, making it challenging even for the most powerful computers. But why does this increase in complexity occur? To understand this, let's take a detour into the realm of geometry. In a high-dimensional space, most of the volume is concentrated in the corners of the space, far from the center. This means that high-dimensional data is inherently sparse, with most data points located far from each other. This sparsity makes it difficult to find patterns in the data, as the distance between data points becomes less meaningful. Moreover, as the dimensionality increases, the difference between the nearest and farthest data points tends to converge. This phenomenon, known as the concentration of measure, further complicates the pattern recognition task in high-dimensional data. It's like trying to hear a whisper in a noisy room. The subtle patterns in the data are drowned out by the overwhelming noise of the high-dimensional space. Despite these challenges, researchers in the field are not deterred. They are actively developing advanced algorithms and techniques to tackle the curse of dimensionality. One such approach is dimensionality reduction, which aims to reduce the number of dimensions while preserving the essential structure of the data. Techniques like principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, are commonly used. While the curse of dimensionality presents a significant challenge, it's not the only hurdle in hyperdimensional computing. The theoretical foundations of this approach are still being explored, with many unanswered questions about its principles and mechanisms. For instance, what is the optimal dimensionality for different tasks? How can we best encode and manipulate data in high-dimensional space? And how do we interpret the results of these high-dimensional computations? These questions form the crux of ongoing research in the field, driving the quest for knowledge and innovation. The climax of our journey through hyperdimensional computing is not a destination, but a challenge, a call to arms for researchers and innovators. The potential of this approach is vast, but so are the obstacles in its path. However, these challenges can be overcome with continued research, collaboration, and a healthy dose of determination. The future of hyperdimensional computing in AI is not yet written, but with every step we take, we're writing it ourselves. Despite these challenges, the potential of hyperdimensional computing in AI is undeniable. The key to unlocking this potential lies in continued research and collaboration. By developing more efficient algorithms, exploring ways to reduce computational demands, and conducting practical demonstrations of this approach in real-world AI applications, we can overcome the limitations and realize the full potential of hyperdimensional computing. Interdisciplinary collaboration is another crucial element in this quest. Insights from fields like mathematics, physics, and neuroscience can shed light on the principles of hyperdimensional computing and guide its application in AI. By bringing together experts from different fields, we can foster innovation and accelerate the advancement of this technology. Moreover, integrating hyperdimensional computing with other AI technologies can lead to synergistic effects. For example, combining hyperdimensional computing with deep learning can result in models that are more efficient, robust, and interpretable. This integration can also open up new avenues for research, leading to the development of novel AI algorithms and techniques. As we reach the end of our journey, we are left with a sense of awe and anticipation. The hyperdimensional computing and AI world is vast and largely unexplored, filled with potential and challenges. But with continued research and collaboration, we can navigate this complex landscape and unlock the secrets of this promising technology. So, what does the future hold for hyperdimensional computing in AI? Will it revolutionize the field as we know it, or will it remain a niche area of research? Only time will tell. But one thing is certain: the journey is just as important as the destination. As we part ways, we leave you with some thought-provoking questions. How will the advancements in hyperdimensional computing reshape the AI landscape? What new applications and opportunities will it unlock? And what ethical and societal implications will it bring? We invite you to ponder these questions and share your thoughts in the comments below. Before we sign off, we'd like to remind you that the world of AI is ever evolving, and there's always something new to learn. So, if you enjoyed this deep dive into hyperdimensional computing and want to stay updated on the latest developments in AI, don't forget to like, share, and subscribe to our channel. And remember, the future of AI is in our hands, and every discovery and every advancement brings us one step closer to that future. Thank you for joining us on this journey. Until next time, keep exploring, learning, and pushing the boundaries of what's possible with AI. Thanks for watching.